COVISCAN is a one-stop shop for all necessary COVID-19 data and analytics for pedestrians. To achieve our project goals, we developed requirements to meet our users' needs. We will talk about our functional and non-functional requirements and how our architecture design decisions were informed by them. To begin, I will explain who COVISCAN's users are. The consumer, the average citizen who needs COVID information in order to conduct daily activities outside their homes. Business users who have opted to utilize the product to increase safety for their employees or as part of their business activities. Government and contractors, so government workers or contractors that rely on COVID data from our product. Starting with functional requirements, we have high priority functional requirements, meaning that they are essential to our product. The client must be able to select a region to search. This means visually, where they interact with the map, or directly where they input their location, address, or postal code. In order to fulfill the needs of our users, the system must be able to store collected data on a centralized cloud database. The system must also be able to retrieve the relevant data from the database. By relevant, we mean that the data is within the selected region that the client has chosen. The system must then take this relevant data and generate analytics, data visualization, and also an overhead heat map. Our final high priority functional requirement is that the system must be able to update the current analytics, data visualizations, and heat map to match the user selected region. We will now cover the medium and low priority functional requirements. The client must have access to all of the following COVID-19 data: general population traffic, reported COVID-19 cases, and location busy times. The system must be able to provide data for any location in the world. This is within our deployed regions, starting with Canada. Since our product is most likely being used by mobile phones, the client must be able to access the system via a mobile browser. The user interface and functionality must be consistent whether it's on mobile or a desktop. For ease of use, upon opening the web app, there should already be analytics and visualizations based on user agent information. We will be using cookies to achieve this. Finally, the client must be able to have the option to toggle visualized data, including heat maps, location busy times, and COVID reports.
Non-functional requirements refer to the quality attributes of a software system. For our system, we selected non-functional requirements based on the listed subcategories. Under performance, we specify metrics such as system response time, age of analytics data, as well as concurrency accepting multiple user requests. For security, the system must encrypt any client-system interactions following security standards. The system must also be protected against known vulnerabilities such as SQL injection. Privacy-wise, users must have their personal identification secure from security breach. For usability, the system must have an intuitive user interface and require few clicks to obtain results. The application must be accessible through assisted readers and include other accessibility functions such as tooltips, alternative text, and tab highlighting. For reliability, the system must always be accessible within deployed regions with minimal maintenance and downtime. Regulatory-wise, the application data must be sourced within legal boundaries. For availability, the application must be free to use. For maintainability, the endpoint data will be consistent collection, aggregation, and analysis-wise, and the application data must be updatable with over-the-air updates and no downtime. For scalability, the system should collect and provide data for any future possible regions, and the capacity of the system can be improved just by increasing server or storage plans. And finally, data integrity. Analytics data is sourced from reliable and trustworthy sources. System summary. Daily COVID data from several sources are presented alongside analytics to users based on their region in an aggregated and visualized manner. The two interacting parts making up the system include front-end and back-end. For the front-end, this includes the client browser displaying a map with an overlay heat map, as well as visualized data and analytics. For the back-end, this includes managing, compiling, parsing, and generating analytical data, as well as data storage from various sources.
Considering the requirements and users of the system, the best architecture style for COVISCAN is a 3-tier client-server style with a mix of model view controller. The client-server style was chosen for the following reasons. The system is handling distributed data. The client can be lightweight and work via server requests. There is business logic such as analytics and COVID data which needs to be separated from the end user. The system can mix end user platforms like mobile and desktop, and the system can be scalable as more regions are supported. The model view controller style manifests itself in the client. The view and controller are the end user's main interaction with our service, and the model keeps the client and server communicating. This approach is chosen for the following reasons. The end user can have many views with the potential for adding new views as well. The end user is removed from low-level operations, and future interactions with server data can be improved and/or modified. Other architecture styles that were considered are repository style and publish-subscribe style. While repository style is efficient at storing big data and is easy to manage, COVISCAN has no need for complex data computation, long-term storage, or saving a system state. COVISCAN is a request-based system. This is where publish-subscribe would be advantageous. However, the client doesn't request data at a fixed period, it needs it upon request, and it needs to be served at that time. A publish-subscribe relation could be detrimental as extra client-side logic would be required to filter and manage the subscription.
Here's an overview of our top-level architecture derived from a client-server and model view controller style in order to best deliver the required functionality. Overall, the system architecture comprises of 3 subsystems which carry out these tasks: client interaction, data retrieval and normalization, and finally visualization and analytics. Each subsystem may not necessarily interact with all the other subsystems, depending on the data and the control flow. The model view controller style manifests itself in the client, while the interaction between the client and the rest of the system can be seen as the client-server separation. As the user's interface, the client is responsible for managing the data requested by and presented to the user. It does not store any large amount of data. The data retrieval and normalization subsystem is tasked with pulling data from third-party APIs, filtering, and then parsing it into a format usable by the whole system. Subsequently, it will store the relevant data on the system database. The visualization and analytics subsystem will leverage the stored system data, the client requests, and more third-party APIs to deliver the requested client data, visualization, and analytics.
These are the subsystem interactions. Region preferences will be set by the user and user device. These preferences determine what data is used for presentation. Presentation comes in the form of visualization and analytics. Notice that the visualization and analytics subsystem is broken into 2 components. This is because visualization and analytics provide separate customer value. Visualization is an explicit representation of the current situation, while analytics goes a step deeper. Analytics can provide descriptive, prescriptive, and predictive insights based on the current situation. Visualization and analytics components will interact with region preferences. This information is used to get a range of COVID-19 information from a database. This data is transformed through interactions with external libraries. Normalization deals with incoming data. The purpose is to make the data usable for visualization and analytics libraries. The organization of subsystems is driven by keeping code dry and good design through maintainability. Maintainability is achieved through low coupling and high cohesion. We want to minimize dependencies. Subsystem interaction should only be done when necessary. We also want to group tightly related components together. Elements that work together to provide specific functionality should be componentized.
As an outline of the client workings, the sequence and activity diagrams shown here outline a typical function. A user sets their parameters through the client, including the region, and the client will request the data for that region. That is the boundary of the client, as in it can only await the response. Once the requested data comes back, the client then uses it to create a visual display for the user. This is a subsystem because in spirit of the client-server style, the client is meant to be isolated from the server processing. The data retrieval subsystem functions periodically when new data is needed to populate the system. It is therefore responsible for searching and requesting relevant data from third-party APIs regarding COVID. The pulled data is filtered, parsed, formatted, and then stored on the system database for system use. Since this task is periodic, it doesn't really influence the client or visualization/analytics subsystems. That's why it's segregated as its own subsystem. This last subsystem comes into play when communication between the client and stored data is necessary. Once a client requests data, the visualization and analytics subsystem will query third-party APIs to provide their services on our data. These services could include analytics, heat mapping, or visualization. This subsystem then organizes the API data and forwards it to the client for display. Seeing as the facilitation of data to the client was necessary in our three-tier client-server architecture, this subsystem was divided to handle that work. It is the most important and the most comprehensive subsystem.
Concurrency. Concurrency is present during the generation of analytics, visuals, and when the system is retrieving data from the database. Specifically, when the client selects a desired location, the system creates parallel worker threads to search for matching criteria in the database concurrently. The results of these searches are then merged to form the overall results of the search. Additionally, once the results are obtained, the system sends this data to each individual analytics and visualization API concurrently.
Lessons learned. It was important to factor in the user requirements to help us decide our architecture. As mentioned, we decided against using the repository architecture because we understood that our users would not benefit from having long-term storage or complex data computations. Another example of user requirements affecting our design was user accessibility. Our application provides data in various formats with text, visually, and text-to-speech. Designing around our users was a large consideration for our choices.